In this video we will look at Lenz's law primarily, but also of course we will have to talk about Faraday's law at the same time. Now here we have a setup. We have a solenoid, a load of coils of wires connected to a galvanometer. Now galvanometer is a very sensitive ammeter. At the moment it's sat in the middle at 0, and it can swing either negative in that direction or positive in that direction. Now what we're going to do is, at the moment the magnet is still and there's no reading, it's reading 0. So in a moment we're going to move it, or imagine we're moving it towards the coil and see what happens. So here we go. Let's say we now move it towards the coil, and whilst it's moving towards the coil we will get an EMF induced. The EMF will be induced because there is a changing magnetic field strength. So imagine these are the magnetic field lines coming off it. Okay. As it gets closer, the density of the lines near the coil will increase, and the magnetic field strength by the coil will increase. Therefore, there is a changing magnetic field strength. So, changing magnetic field strength from Faraday's law, EMF induced equals the rate of change of flux linkage, or as I often write it, the change in NBA over T. What is changing is in fact the magnetic field strength is changing. But the area and the number of coils doesn't. So magnetic field strength is changing, it will induce a current. Now in which direction will it induce? Now, Lenz's law says that the induced EMF is in such a direction as to oppose the motion causing it. So as we've got a solenoid here, what will be set up? At this end of a solenoid, there'll be set up a north pole, and this end, therefore, a south pole. So a north pole will be set up on this solenoid, and of course that will resist the motion of the magnet moving towards it. Now, if there's a north pole set up, you will see that by the idea, if you're looking from above onto the wire, and if you imagine you've got an end like that, you'll find that the current will flow in an anti-clockwise direction. Okay, anti-clockwise direction given by that. So therefore, if it's flowing in an anti-clockwise direction, we should see that it's flowing in this direction, and the galvanometer should deflect in this direction whilst the magnet is moving towards it in that direction, like that, with velocity v. Okay, that's one situation. Now, as soon as it stops moving, as soon as the magnet is still, and as soon as v equals 0, the arrow will go back to 0 again. Because even if the magnet's in the middle there, if it's not moving, there will be no induced EMF. Okay, so we've moved it a bit closer, and then it stopped. Okay, so what's going to happen next? Well, next what's going to happen is, let me rub this off, is we're going to move it away from the solenoid. Okay, so let's draw this up together again. So now our magnet here, north pole this end, south pole this end. This time it's going to be moving with velocity v in that direction. So what's going to happen now? Again, go back to Lenz's law. The EMF is in such a direction as to oppose the motion causing it. It doesn't want change to happen. So it doesn't want change to happen. What change is going to happen? Well, the magnetic field strength is going to get weaker as you move the magnet away. So to stop the change happening, the solenoid is going to create... I've drawn my magnet the wrong way around. I'll swap poles. Let's rub this out again. So my magnet It's still north end here, still south end here, but this time it's moving in that direction. So to oppose the motion, last time, as we're moving it towards it, it created a north pole this time. This time it's going to create, at this end, a south pole to stop the magnet moving away, and therefore a north pole at this end in the solenoid. It's like acting like a magnet. Okay, so the south pole there, and if you look at here, it will be in a south. So we draw a south to show you an S, and draw arrows on the end to show you the direction of the south pole is in a clockwise direction. So if we look from the top, the electricity is moving in a clockwise direction, like that. We'll see that this time the current is flowing in this direction there. Okay, so therefore this time the galvanometer will be deflected in the opposite direction. So while the magnet is moving away, it'll be deflected in the opposite direction was before. And what's changing again, what's changing as before to produce EMF is the magnetic field strength B there. It is the changing magnetic field strength which causes the change to cause the EMF.